we will present DUNE, distributed inference in the user plane. Origami aims at spearheading the next generation of mobile network architecture, overcoming 8 factual barriers to ensure a successful 6G future on radio access networks, transport, and core levels. This work addresses barrier number 4, underutilized modern programmable transport, and responds to the use case called effective, distributed, and streamlined access to user plane computing capabilities. This network intelligence solution corresponds to Origami's compute continuum layer, innovative architectural component for 6G systems, envisioned to optimize network operations according to characteristics of the underlying infrastructure. Specifically, embedding ML models into programmable network hardware is a hard task, as it requires tailoring the design and operation of the original models to highly constrained targets. Programmable switches and smart NICs have severe limitations in terms of compute capabilities and memory resources, in addition to internal architectures that are purposed for packet forwarding and not inference. Previous solutions about in-network ML-based inference have invariably sought to implement monolithic ML models into a single network equipment. Our proposal is to decompose the operation of the original monolithic ML model into submodels that can be deployed as P4 programs into different devices and jointly execute the target inference task. This lets each device solve a portion of the problem and leave the rest to the downstream network. While the concept of distributing the model across the network seems simple, its realization poses a number of challenges. How to best decompose the original ML model to preserve accuracy while keeping the submodel resource usage under control? How to order the resulting submodels? How to ensure automation of such a decomposition process for an arbitrary inference task, and this should be done in line rate operation. The workflow begins by extracting historical measurement data about the target inference task, suitably labeled for supervised learning. In the first stage, we train the most accurate ML model possible with no requirement on the model type. The result is a monolithic model. Then, we extract the importance of each feature for each class and format it into a matrix format. In addition, we encode the accuracy into a vector F. These two variables are used to generate an instance of the SPP, which aims at splitting the classes set into smaller subsets, where members in each set have both similarly important features and accuracy. The result is a partition P. With the information of each set and the features used in it, we train hardware-aware tree-based models for each class. We use a grid search over the hyperparameters to maximize accuracy. The order in which the submodels are placed will influence the accuracy due to confusion between classes. To perform this task, we formulate and solve another optimization problem. Finally, we generate P4 programs for each model. We implement DUNE using P4 and deploy it on a platform with 5 Intel Tofino switches for attack detection and device identification use cases. Benchmarks are the state-of-the-art monolithic models. Now we will see the demo. We compare our solution DUNE with 3 different benchmarks: No Inference, Musica, which is a packet-level solution, and Joule, which is joint packet and flow-level solution. In the case of No Inference, all the switches forward the incoming packets. We do not implement any inference model in any switch, so we do not calculate the performance scores. But the latency for inference across 3 switches is around 850 nanoseconds. Musica runs inference for every packet individually, and it is a monolithic solution. The classification results per packet is shown with different colors in the animation.
The micro F1 score of Musica starts around 70%, but then it drops significantly through the experiment. The overall scores are also very low. It has around 50% macro, 41% micro, and 37% weighted F1 score at the end. Musica adds additional 17 nanoseconds latency to no inference case, which is totally negligible. DUNE is a joint packet and flow level solution. It is deployed into one single switch. It classifies the early packets individually, and through the early packets, it collects flow level features. Whenever the flow level features are ready, the flow is classified. Then the results are stored in the forwarding table so that the consecutive packets can only go through the forwarding table with no inference and tagged with the class of the flow. Compared to Musica, DUNE has higher and more flat micro F1 score. Overall, it also outperforms Musica in terms of all the metrics. Its latency is just around 140 nanoseconds higher than Musica. DUNE performs joint packet and flow level inference across 3 switches. The models in every switch focus on a specific subset of classes to run the inference as shown with different colors in the inference block. If a packet or a flow are classified as others, shown in gray, it will be directed to the downstream switches to be classified. Whenever a flow is classified, we store the result in forwarding tables for the consecutive packets to be tagged as explained in DUNE. In terms of micro F1 score, we can see a flat performance through the experiment, but higher score compared to DUNE and Musica. Overall, DUNE outperforms both Musica and DUNE in all F1 metrics. The reason is we decompose the complex problem into simpler problems where each switch focuses on a different subset of the problem.
In terms of latency, it is comparable with other solutions, and overall, it is around 1 microsecond, which is more than acceptable. DUNE demonstrate higher accuracy than monolithic models, comparable latency, and lower TCAM usage versus flow-level solutions.